the derivation between efficiency, mechanical advantage and velocity ratio of a machine. Okay, machine, you know, a device that makes the work simple. Okay, now there are some terms which we are going to discuss before we are going to derive the relation between efficiency, mechanical advantage and velocity ratio. Okay, now first and foremost thing is that we have the expression small l. Okay, this refers to the load. Okay, load is the resistance which is overcome by a machine. Okay, normally the unit of load is in Newton because it is a type of force. So let's consider the unit Newton. Then second we have E. E stands for effort. Okay, you know, a machine cannot work on its own, it needs some effort. So effort is the force applied on the machine. Okay, the force applied on the machine. Okay, so this is also a type of force, so we will write Newton for the unit. Okay, third is, now we are going to discuss about the mechanical advantage, MA. This is mechanical advantage. Okay, a machine is said to have mechanical advantage if it can lift a heavy load when you are applying a small effort. So the gaining mechanical advantage means you are applying little effort and you are lifting or working a big load. So there you gain a mechanical advantage. So it is defined as the ratio of useful load lifted. Okay, useful load lifted by total effort applied. Okay, so mathematically it is L by E. Okay, L for load, E for effort. Because it is a pure ratio, so it has no unit. Okay, now here we are giving a cross because there is no unit for this, it's a pure ratio. Then we have the small d. Okay, this is called the load distance. Okay, that means the distance traveled by the load. Okay, so whatever is the load distance, that is in meters. These are the units. Okay, fifth, then we have the capital D. This is called the effort distance. Okay, that means when you're putting effort on the machine through some distance, you're doing work. So what is that effort distance? This is capital D. Okay, the distance through which effort is applied, through which effort acts. Okay, so because this is distance, even this is measured in meters. Okay, then we have VR. The VR term is velocity ratio. Okay, so this is defined as the effort distance to load distance. Okay, so I repeat once again, it is the ratio of effort distance by load distance. Clear? So this is also a pure ratio having no unit because it is the ratio of capital D by small d. Okay, so no unit means I am putting a cross. Then we have the work output. Okay, work output means the work done by the machine. Okay, so work output is work done by machine, and this is equals to the work output depends upon the load into load distance. Okay, so mathematically we can write it as small l into small d. Okay. So because this is work done, so we shall write it in joules. J for joules. Then we have the work input, because you have to put some work on the machine, only then the machine can do the work in return, that is the output. So work input means work done on the machine. Okay. So this is equals to effort, because you are putting effort, which is a type of force, multiplied by the effort distance. Okay. So this comes to E into capital D. Okay. Now this is also a type of work, so we shall express that is joule. Now we are coming to efficiency. Okay. The efficiency of a machine is simply the ratio of work output to the work input. So the first expression is work output, that is work done by the machine, to the ratio of work input, that is work done on the machine. So this is work done by the machine, this is work done on the machine. Now because work output is load into load distance by effort into effort distance, okay, mathematically we express efficiency as the symbol eta. Okay, so this is the symbol for efficiency. Okay, now we can also write efficiency equals to, okay, let's divide this into two parts, small l by capital E into this is small d by capital D. Shifting this fraction on the left hand side, we have efficiency into capital D by small d equals to small l by capital E. Okay. So here we have the velocity ratio already discussed over here, and this is the mechanical advantage. So ultimately we have got the expression efficiency into velocity ratio equals to mechanical advantage. The symbols have already been discussed over here. So ultimately we have the expression efficiency equals to mechanical advantage by velocity ratio. So this is the derivation for expressing the relation between the efficiency, mechanical advantage and velocity ratio. Okay. So you can represent this as a symbol eta, that's a Greek letter, which is equal to ma by Vr. Okay. So this is about the derivation. So you have to describe all the parameters involved in this. Okay. So I hope you enjoyed this derivation and it's very clear for you to follow. Okay. Thanks for watching.